Okay, so we are going to be doing the rolling bowl lab today. So go to classwork, and if you need references, there are weekly slides where there always are as 0 under week 6 ball on the floor. So this has the intro slides and just some basic information. But if you don't want to look at that, that's fine. We'll look at it tomorrow. Today, go to number 1, rolling ball lab. Click on the Desmos. Open it up, make sure it says your name, not a different name, and that it says welcome to the rolling ball lab. Click go. Okay, to get started, let's view what velocity is. In the text box below, write the definition of velocity. So velocity is speed with a direction. Okay, once I'm done with that, I can click share with class. Next. We are going to use a rolling ball to model a car's motion. Watch the video, then make the following prediction. How far will the bowling ball travel in 6 seconds after it rolls down the low ramp? So how far, so what's the distance? It rolls in 6 seconds. So we need to see this. How far? Okay, so I see that it's past 3 meters and 2.5 seconds. So I need to guess how many meters. So I can double that, I can do whatever. So I'm gonna put, I don't know, maybe 6.5. Just whatever you think, share with class. Next. Okay, remember that we are making predictions. There are 4 different patterns that we know. Okay, the first one is horizontal. Okay, this means that when x doubles, so when time doubles, the distance will always stay the same. Our linear pattern, okay, which means that when time doubles, distance will double. Our quadratic pattern, let me change the color, okay, which means when time doubles, distance will quadruple. And then the last one that we haven't learned is, it's called inverse. When time doubles, distance will be cut in half. So remember, pick one line, only one of these colors that you think represents, that is going to represent this graph or this pattern of time and distance. And then in here, in the text box below, identify the independent variable and the dependent variable from the research question. So how does the time of rolling affect the distance rolled? So for those of you who don't remember, okay, let's do this. So how does time, like we want the word affect, okay? And then the word, okay, let me try to move this. There we go. Time and distance. This one, time is what we are changing or we are paying attention to. And because we are paying attention to time, that makes it our independent variable, which means distance, okay, is our dependent variable. So when I write, my, let me write this down so that we can remember. When I write my hypothesis, it says, I claim that as time increases, distance will, and remember, you need to tell me, is it going to increase, decrease, or stay the same? Then you need to tell me why. Why do you think that's going to happen? Remember, our 2 increasing lines are the red one and the purple one, which is the linear pattern and the quadratic. The blue line is horizontal, which tells us that it's going to stay the same. And then The orange one is the one that tells us that it will be cut in half. After I do that, okay. Oh, oops. This is where you write this is where you actually draw the line. Sorry. You're going to tell me, like, what do you think is it? Is it going to be horizontal? Blah, blah. Tell me why. I think it will be inverse. Because da 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 da. Like, give me your opinion. Like, any of these. Which one will it be? And then tell me why. After that, we're going to collect data. So use a video on the left to take data about a ball rolling along the ground. Only complete data for one video assigned to you. So I'm either going to do it for the low ramp or the high ramp. Let's say I assign that we are going to do the high ramp. So I need to watch this video and I need to figure out in seconds how far the ball travels. So you can see, I'm just going to watch it. Oh, it takes less, this video only goes to less than 2 seconds. So maybe I will do 10 seconds or 10 milliseconds, 20 milliseconds, 30, 40, 50. You can choose whatever you want. I'm just choosing that because then I can kind of see. So, so I need to find, and that's the nice thing about this video is that you can adjust it however you need. At 10 milliseconds, oh, that's not even clear. And that's another thing too. So let me play it again. These are half. It looks like the meters are going up by 0.5. So if I go back, at 10 milliseconds, it is between 0.5 meters and 0 meters. So it is like right here, I'm like, this isn't going to be super accurate. So this is where I'm going to have to do some deductive reasoning. I'm going to say like maybe it's 10, 20, 30, 40, 50 right here. So I'm going to say it's about 0.25 meters. And then I'm just going to keep doing this lab. And let's just say that at 2, let's see. Maybe what I'll do is, maybe it's too hard for me to, do it like that. So I'm going to wait for it to get to 1 meter. At 1 meter, I'm at 44, or, oops, sorry, 0.44 seconds. And maybe that's what I'm going to do. Maybe what I'm going to do is, instead of trying to figure out the different time first, maybe I'll just do it by distance. So at, let's see, where was the ball? About there, 1.5 meters, and my time was 0.66 seconds. All right, and then I can do it that way, which might actually be easier. And once I do that, I can go over here, and remember, I'm moving the A slider to figure out which of these lines are my correct line. Once I do that, I'm going to say, oh, my pattern was whatever, and then I am done for the day. So we are going from part 1 to part 7.